All right, this is a solution to particle kinetics number 23. This is the one where you have a block sliding along a wall. So this block has a mass of 2 kilograms. Um, and uh, it's sliding down the wall at this instant. Okay, so that's the direction of motion at the instant. And the reason that's important is because the direction of the friction force is always opposite the velocity vector. So this problem would look different if this block was sliding up at this instant. And then there's an external force that's applied. This way it has a magnitude of 300 newtons. And it makes an angle of 30 degrees with the horizontal. Okay, well, this is a sliding problem, and in any rolling and sliding problem, I said get in the habit of just using a coordinate system that's rotated a certain way, where the y-axis points straight out of the surface. So that's the y-axis, and the x-axis just follows based on that. It's just going to be a rotation of the usual coordinate system. Okay, now that's a funny coordinate system. You could, of course, I mean, any of these problems you could do in a normal coordinate system. This would be easier than a lot of them to do in a normal coordinate system because it's just a 90-degree rotation. But if you do this, a lot of the stuff just keeps looking the same in every problem. And that's a nice, that's sort of the benefit of this. Okay, so what do we have? Let's draw a free body diagram of the block. The forces that we have are a weight force. That's 2 times 9.81. So 19.62 newtons down. And then we have this external 300 Newton force over here. And now we have the contact force with the wall, which is made up of a pushing force and a friction force. The pushing force is this way, and I'll call that N. That's the normal force. And then the friction force is opposite the direction of the velocity. The velocity is down, so the friction force is up. This asks you to solve this problem for 2 different coefficients of friction. I'm going to just do like part C. I'm going to solve for the acceleration. Oh, it actually asks you to do it 3 times, one without friction. So this friction force would just be gone, and then 2 different coefficients of friction. I'm going to do the one in part C. So the coefficient of friction is 0.5. So that means that this would be 0.5 times N. And that's it. That's all the forces acting on it because we've gone all the way around the boundary. Now all we have to do is represent all these in this rotated coordinate system. Usually in a rotated coordinate system, the one that's a little confusing or a little trickier to calculate is the weight force. That's the one where you have to use cosine and sine. But in this case, because our coordinate system is just rotated, some number of 90 degrees from our original one, the weight force is just in the negative x direction. So that's easy to figure out. The one that's harder to figure out is the 300 Newton force. So let me draw that out. Okay, so our coordinate system has x like that and y like that. And the 300 Newton force acts this way, where this angle is 30. So now to figure out the angle, theta, we go counterclockwise from the x-axis. So we go 90, 180, 270, plus another 30 is 300. So you could represent that as 300 times cosine and sine of 300 degrees, or you could go negative 60, does the same thing, gives you the same numbers. Okay. So Newton's second law says 300 times the cosine of 300 degrees and 300 times the sine of 300 degrees plus this weight force I said was in the negative x direction, so negative 19.620. N is where it always is, the positive y. The friction force in this case is in the positive x, so that's plus 0.5 n 0. And all these are equal to the mass times the acceleration, which is a0, like it always is if you use a rotated coordinate system. Okay, so let's see. 300 times cosine of 300 and sine of 300. That vector gives you 150, negative 259.81. Plus negative 19.620 plus 0n plus 0.5n 0 is equal to 2 times a0. All right, so how many variables do we have? How many equations? Our two variables are a and n, and we have two equations, so we should be able to solve it. The way to do this with these friction problems is pretty much always to use the y equation first to solve for n, and then plug that value of n into the n and the x equation. So the y equation ends up telling us n is equal to 259.81. And that means that the x equation says 150 minus 19.62 plus 0.5 times 259.81 is equal to 2a. Okay, so let me plug this in. And so this says that the acceleration is positive 130.14 meters per second squared. Okay, well, what does that mean as far as a direction? Well, in Newton's second law up here, we already represented the acceleration vector as a0. So if you plug this in, it means that the acceleration vector is positive 130.14. And now we have to think about what that means. So this is meters per second squared in our coordinate system. Okay, well, our coordinate system has the x-axis pointing up. So that means that this is an upward acceleration with a magnitude of 130.14 meters per second squared. So is this object speeding up or slowing down? Well, we know that the velocity is in the negative x direction, or down. We know that the acceleration is in the positive x direction, or up. And so this is slowing down. It's actually slowing down really, really quickly. You know, that's 13 times the free fall acceleration of gravity or something. But that's because friction and the weight are both working in the same direction, and the friction is really high. So, okay, that's number 23.